Hello and good afternoon. This is Craig Kosminski with your pre-lab video for experiment number 5, thermometers and heat capacity. If you have not done so yet, please pause this video and read through the entirety of experiment number 5, including the introduction, the procedure, the calculations, as well as the online lab report considerations. One of the most important parts of this process is actually looking at the questions that you'll be answering on your lab report. Take a look at any tables and questions that accompany the lab report so that you can be prepared in advance to answer these questions after collecting your data and doing your data analysis. One important note of distinction is that on this lab report, not only do you have a specific data table where you will be recording your data, but you actually have uh, separate, excuse me, a separate page in your lab report where we are asking you to conduct your actual calculations. So on page 49 of the manual, you will see that you have your data table. And then on page 52, you'll see where we actually want you to show the calculations. And if you have any questions about that, please be certain to ask your lab instructor or lab assistant. So, if you were to think about the purpose of this week's experiment and explain it to, say, a 8 or a 10-year-old, what would you say is actually happening in this week's experiment? It's really important that you consider this kind of overarching view of the experiment before you enter the lab, because you will have a more positive and bountiful experience if you come into the experiment having a general idea of what is happening. And so, one of the purposes of this video is to help you reveal that information to yourself. And so, what I've attempted to draw here on your screen is an example of what tomorrow's experiment is going to look like. And so, we'll begin by saying that we have this device. This device is a calorimeter. It is consisting of an external cup and then an internal cup. And between that, is foam or styrofoam insulation. And so this is a highly insulated device that we are going to attempt to use to determine the heat capacity of different elements. And so what I have here is a red metal cylinder. And I have the equation that is showing how we would calculate the energy that is going to be lost by that cylinder when we add that cylinder into the water, which is located inside of our calorimeter. Now we're going to add the cylinder into the water, and we are going to observe that the temperature of the metal cylinder and the water are going to come to a point of equilibrium. When this equilibrium is reached, we will measure this by determining the maximum temperature of the water inside of the calorimeter. We'll be able to conduct a basic calculation to determine the heat capacity, that is our C sub m term in our equation, of any particular unknown metal. And so we'll have a group of unknown metals, and your goal is going to be to identify the unknown metal by calculating its heat capacity. So we'll go into a little bit more detail on these calculations on the next slide. But in review, we have our hot or red metal, and then we have our cool blue water. And again, we can measure the heat gained by the water by taking the mass, multiplying it by the heat capacity of water, and multiplying it by the change in temperature. And we're going to do just this. On the next page, you'll see an explanation of some of the equations that are going to be used in this lab. And so we have our general heat energy equation listed here at the top, where the heat energy is equal to the heat capacity of a substance multiplied by its mass, multiplied by the change in temperature. And so if we want to calculate the heat gained by water, that's delta Q sub G, that's heat gained, we would take the heat capacity of water, which is given in units of 1 calorie per gram degree Celsius. We'd multiply it by the mass of our water, and we would multiply it by the final temperature of the water minus the initial temperature of the water. This is the delta T term that I've been referring to. Now, when a substance is at equilibrium, we can say with confidence that the sum of the heat gained and the heat lost should be equal to 0. Now, there's a big assumption here, and the assumption that we're making for this calculation is that all of the heat energy lost by the metal is going to be gained by the water. And so I want you to think about that, think about what you're learning in lecture, and actually think, is all of the energy from the metal going to be perfectly converted into energy of the water? That is, are there any steps along the procedure that you have read at this point where I may lose heat from the cylinder and that heat is not directly transferred to the water? Now, for the purposes of our calculations, we are going to assume that this happens perfectly. And so we will say with confidence that the heat lost is equal to the opposite of the heat gained. And so rearranging this equation, delta QL equals negative delta QG, and substituting terms in for delta QL, we can calculate or rearrange for solving of the heat capacity of the metal. That's C sub m. Now, this is not shown in its entirety. So what I've attempted to do over here on the right-hand side is to show this. So I'm going to supplement this now. So the heat energy lost is equal to the opposite of the heat energy gained. And so if I replace delta QL with the information for the metal, it's the heat capacity of the metal times the mass of the metal times the final temperature of the metal minus the initial temperature of the metal, excuse me. This is set equal to the heat capacity of the water times the mass of the water times the delta T of the water. Now, if you're paying attention, you've probably already figured this out, but let's get a new color here. Nice little purple. The final temperature of the metal is also going to be the final temperature of the water. This is our equilibrium temperature. And so what I'm going to do is I'm going to circle now the term that we're going to solve for. We're solving for C sub m, that is the heat capacity of our unknown metal. And to solve for this, what we're going to do is we're going to divide both sides of the equation by the mass of the metal times the change in temperature of the metal. That's T sub F minus T sub Im. And so if I divide the left by that, I also have to divide the right by that. T sub F minus T sub Iw. And so when I divide both sides by this term, I'll be left with C sub m on the left. And I can set this equal to my delta Q G, negative delta QG, which is the product of these three terms. So you'll notice in the first step here, I wrote delta Q G. And then in the second step, I expanded this to show you how we calculate delta QG. It's negative CW times MW times TF minus TIW. So you can either use the term that's given here as negative delta QG, or you can write it all out. I'm going to write it all out so it's obvious. Negative CW times M sub W times T final minus T initial of the water. That's the W. And we're going to divide that by our M sub M, that's the mass of our metal, times the change in temperature of the metal. So that's T final minus T initial of the metal. And so there is a subtle distinction between the delta T's. On the top, it's the final temperature or the equilibrium temperature minus the initial temperature of the water. On the bottom, it's the final temperature or the equilibrium temperature minus the initial temperature of the metal. So this is a very subtle distinction, but one worth noting here. After you go ahead and calculate the heat capacity of the metal, we will then compare those heat capacities to our table of known heat capacities for our metals. And this is going to be the way in which we attempt to identify those metals. And we're going to put our claims from our experimental data right here on page 47, where you're going to calculate the atomic weight using the heat capacity. And then you're going to attempt to identify the unknown sample. If you only were to compare its atomic weight to the periodic table, that happens here. And then in the last column, you're going to attempt to identify the unknown metal based on the heat capacity. And you're going to identify that substance, and then you're also going to give a short description or reasoning. And then finally, here and on the next page, you're going to talk about the procedure itself. Now, one important part of the procedure that I didn't talk about is that every student is going to be expected to choose the copper colored cylinder uh, out of the group. So out of the group of cylinders that you have to choose from, most of them are silver colored or gray colored. There's only one cylinder that is copper colored, and each group has to choose the copper colored cylinder in order to be able to successfully answer the lab report questions on page 48. Finally, there are some exercise worksheet problems. I'm going to zoom in on our notebook here to try to help you get started on these. In question 1, it says calculate the amount of heat energy that is required to warm the water for your shower. If you assume that you have 10 gallons of water and we are going to warm the temperature of the water from 15 to 45 degrees Celsius. So if I want to calculate the heat energy required, I know that it's equal to the heat capacity of the water times the mass of the water times the change in temperature. Okay, so that's our delta T. So one thing to think about is that you know from the experimental data already where our heat capacity of water is. It's 1 calorie per gram degree Celsius. Now, the great thing about looking at this constant here is that it gives us the units that we have to use for the rest of our equation. So I know that my final answer is going to be in units of calories. So that's the unit for our energy here. So the unit for mass that I'm going to be using is grams. So I'll have to convert 10 gallons of water, which is a volume, to units of grams, which is a mass. So here you're given that conversion factor for every 1 gallon. There are 3,780 grams. And then for delta T, to answer this part of the question, you're going to have to uh, use the change in temperature in degrees Celsius, so 45 minus 15. So just to get you started on the exercise worksheet, there are a few problems. I would recommend at least writing down the equations that you think you will need to solve these problems on the exercise worksheet before coming to lab tomorrow. Some of these problems are easier than others, so just having a good idea of where to start on each of these will be a good start for you. And my final comment is for question number 4, you have to be careful with your units. So for part A, it says calculate the kinetic energy in units of joules. So hopefully you remember the equation for kinetic energy is 1/2 mv squared. It then says calculate the gain in heat energy in the brakes. And what we are asking you to do here is to assume that all of the kinetic energy that is lost by the car, so the kinetic energy of the car that it loses when it stops, is perfectly converted into heat energy. That's our delta Q. And so the most important part, all you're really doing here is you're converting units of joules to units of calories from A to B. So you're going to convert part A into calories, assuming no heat loss. And this will set you up in part C to then determine the increase in the temperature from the heat energy. So here you have your delta Q, and then below you're given the mass of your metal. You're assuming that the brakes are completely made of iron, and you're also given the heat capacity of the metal. And so you can determine the increase in the temperature or the delta T if given all of this information. I hope this video is helpful in preparing you for this week's experiment. And if you have any questions, as always, please reach out to your lab instructor. I look forward to seeing all of you this week, and have a great day.